Hello class, welcome back. Today I'm going to be going over the test 2 review, and test 2 goes over chapters. It goes over chapters 2, chapter 2, 6, and 7. Where chapter 2 was energy and momentum, chapter 6 was heat and temperature, and chapter 7 was thermal energy and phases of matter. All right, so let's get right into it then. So number 1 on the review says a freight train rolls along a track with considerable momentum. If it rolls at the same speed but has twice the mass, its momentum is, well, this one just basically uses the momentum equation, right? So basically it says it has some considerable momentum, so it has some mass and velocity. And let's say we keep the velocity the same and we double the mass. How is that going to affect the momentum? Well, so now we have 2 times the velocity, and let's call this momentum 2. Well, basically, since the mass is multiplied by 2, and this here basically gives us the original momentum, the new momentum is just doubled, because this right here, mv, gives you the original momentum, and then we times it by 2 because the mass was doubled, and that's just going to give you twice the momentum. So twice the mass, get twice the momentum. And same thing, if you have twice the velocity, then that would give you twice the momentum. All right, so number 2 says, what is the speed of a 6 kilogram ball with the momentum of 72 kilograms meter per second? So again, just using the momentum equation, we're trying to find the speed. So speed is going to be equal to momentum divided by the mass, where the momentum is 72 divided by a mass of 6. And 72 divided by 6 is what, 12, right? So it's going to be 12 meters per second. Cool. So for number 2, the answer is going to be C. Number 3 says a karate expert executes a swift blow and breaks a cement block with their bare hands. The magnitude of force on their hand is, well, this deals with impact, right? And the impact equation is given by force times time, which equals the change in momentum, right? Yeah, so this is basically the impact equation. So you might think that you actually need this equation for this problem. And so since it says here, she breaks the cement with her bare hand, magnitude of force on her hand is what? So it's asking about the magnitude of force on her hand, not necessarily the force that she applies to the cement, right? So we actually don't even need to use this impact equation. This is actually just Newton's third law. This is Newton's third law, which says every action has equal opposite reaction, right? Reaction. So basically the action here is her hand hitting the cement. And so the force is her hand hitting the cement. The same thing is going to happen to her hand. Her hand's going to experience an equal but opposite reaction. So actually the answer here is going to be, let's see, the same force that she applied to the block. Yeah, I think it's going to be that one. Or B, 0. No, it's not going to be 0. Less than the force that she applies to cement. No, more than the force. We need more information. So the answer here is actually going to be A, the same force applied to the block. So the same force she applies to the block is going to be the same force that is applied to her hand, but in equal opposite directions. All right. So, yeah, on to the next one. Number 4 says, compared with falling on a wooden floor, a wine glass may not break when it falls on a carpeted floor because A, a longer time to stop, or B, lesser impulse in stopping, both of these or none of these. Okay. So when a wine glass falls onto the floor, we know it's going to break, right? Because the impact is high. Well, not necessarily the impact is high, but actually the force on the wine glass is high because it comes to a stop really, really fast, right? And so if this T, or the time, is lower, the force gets higher. But if it lands on a carpet or something soft like this, the impact is going to be, well, the impact is actually still going to be the same, but the force is going to be less. So the impact is actually the same whether the wine glass falls on the carpet or the wooden floor. What's different is the force that is applied to the wine glass. So actually, the answer here is going to be, it may not break because basically of this longer time to stop, right? Because if T gets bigger, then the force has to get smaller. Because the impact or the change in momentum is going to be the same either way. And so if T gets bigger, then F has to get smaller. So the answer to this one is going to be A, a longer time to stop. Number 5 says, the conservation of momentum is closely related to Newton's what? Well, Newton has 3 laws of motion, right? Because it says either A, the first law, or B, the second law, or C, the third law. Well, the first law is just the law of, write it out here. The first law just talks about inertia, right? The second law just talks about acceleration is given by force over the mass. And the third law is action has equal opposite reaction. So these are the 3 Newton's laws, and which one of these most closely relates to the conservation of momentum, where we know the conservation of momentum basically just means the initial momentum is equal to the final momentum. Well, so the initial is equal to the final. So which one of these seems to be like closest to that there? Well, definitely not inertia. Probably not the second one either. This just talks about acceleration. So that leaves this last one. Every action has an equal opposite reaction. So this one is probably the most similar to the conservation of momentum. So the answer to number 5 is going to be C for Newton's third law. All right. Let's see. Consider a gun with a pellet that is more massive than a gun. The firing speed is greater for A, the pellet, B, recoiling the gun, C, both are the same, or D, none of the above. Okay, so I'm going to try to explain this one as best as possible. I think this is kind of an odd question, but the answer to this one's actually going to be B, the recoiling of the gun. And basically the gun is going to recoil more because the pellet is actually more massive than the gun itself. So you can kind of think about this in terms of momentum, right? So when this gun is fired, we can use conservation of momentum. So the initial momentum is equal to the final momentum. And you can kind of think about this as a inelastic collision, where we know an inelastic collision is when we have two objects, they collide, then afterwards they're stuck together, right? Well, in this scenario, it's kind of like a reverse inelastic collision, because initially we have two objects stuck together, right? And then afterwards we have one object going this way and then another object going the opposite way, which this would be the gun. This would be the gun recoiling, basically. And then this is the pellet. This here would be the pellet being fired out of the gun. So let me see if I can draw this a little better. You can imagine I don't know, something like that, right? So these are the two objects together, where the pellet's inside of there, and the pellet's really, really massive. Really massive, weighs more than a gun. And then after the pellet is fired, the pellet's gonna go this way and the gun's gonna recoil, going the opposite way. Now, since the pellet has such a high mass, the gun is actually gonna recoil more or push back more against the pellet's gonna push back more against the gun because it has more of a mass, basically. And so that's kind of like the best way I think I can explain that. So let's see, moving on to 7 then. 7 says you have two identical freight cars roll without friction towards each other on a level track. One car rolls at 2 meters per second, one moves at 1 meter per second. After they collide, they couple and roll together with the speed of, well, let's draw that out. We have one freight car going this way and has a velocity of, let's say this one has a velocity of 2 meters per second. Then we have another one going this way. Going that way, or to the left with 1 meter per second. And so here, since there are no outside forces, we can use the conservation of momentum, or the conservation of momentum just says the initial momentum equals the final momentum, right? Boom. Initial momentum equals final momentum, right? And let's see, what else? And we know both of these have the same mass. So this one has some mass, m, and this one also has the same mass, m. And this is going to be an elastic collision, right? Because first they're moving separately, and then they're going to collide together and then move in some direction. So let's write out the initial momentum. So we're going to have the momentum for this one and this one. Initial one, which is going to be, well, it's going to be mass times, let me just put a 2 for this one's for the right, so 2 mass times velocity. That's the momentum for the first one. And then this one's actually going to be minus 1 times m, where it's minus because this velocity is going towards the left. So that's why that is a minus. And so then that's going to be equal to the final momentum. So the final momentum is going to be the mass of both of them together. So it's going to be mass plus the other mass. And that's going to give you the final velocity that we're trying to find. Right? So now I could just do the work here. Well, that's just going to give me 1m because those are subtracted. So 1m. This is going to give me 2m, v final. And now these masses can cancel out because they're the same. And I could divide 2 over. So that gives me a final velocity is equal to 1 mass divided by 2 mass. Well, those masses cancel out, so the velocity is going to be a half. And notice that it's a positive half, which basically means after they collide, they're going to continue going to the right, but only going basically half a meter per second. And so let's see the answer options or choices. And it looks like, so for this one, it's going to be B. So the only trick about this one was this minus here. So you kind of have to consider the fact that this velocity is going in the opposite direction towards the left. And so since it's going to the left, this is basically a minus 1 meter per second because it's going to the left. Yeah. Okay, so now let's do number 8. And also notice, I guess the last thing I want to mention about number 7 is the last thing they say, well, if you notice, is after they collide, say they couple and roll together with the speed of, so they're asking for the speed, afterwards. And so let me also do this same problem, but the other way around, because you might have said this one's moving at 1 meter per second, and the one to the right is moving at 2 meters per second. So if you would have done it that way, because somebody might have done it the other way, which still would have been right. There's nothing wrong with doing it this way. Then this would have been the 1 meter per second. So if this one were the one moving at 2 meters per second and this one's moving at 1, well, let me do the math real quick for that and show you that we get basically the same thing speed-wise. So we have this momentum, so we're going to have mass times the velocity, which is 1, minus 2 times that mass, which is just m, going to be equal to m plus m, the final velocity. Well, now this gives us a negative 1, so it's going to be minus 1m equals 2m v final. So then the final velocity we get is basically going to be negative half meters per second. So notice this is the final velocity. And so to get the speed is just the magnitude of the velocity, where this negative basically only tells you the direction. So all this negative means is after they collide, they're going to continue going to the right because this one had more velocity. Okay. So basically, if we would have done it this way, all we'd have to do is ignore the negative because that just accounts for the direction. And so to get the speed of this, we'll just ignore the negative and it's just a half. All right, so moving on to 8. I don't want to take too much of your time, already at 18 minutes. So let's see, number 8 is a 1 kilogram chunk of putty moving at 1 meter per second collides and sticks to a bowling ball initially at rest. The bowling ball and putty move with the momentum of, well, this is more another inelastic collision because you have two things sticking together. So we have putty here, it's moving with some velocity, mass is equal to 1. Right this way, mass equals 1, and its velocity equals 1. That's the bowling ball. They collide, stick together. So now we have the bowling ball with the putty stuck to it. And now they're going to move at some final velocity that way. What the mass here is going to be basically, where's the mass going to be? Well, they actually don't give us the mass of the bowling ball. So it's going to be capital M, write it that way. So again, do my conservation of momentum. initial equals final. Initially, we only have this momentum. So we have 1 times 1, because we're trying to find the momentum afterwards. And just using conservation momentum, we know the initial momentum is going to be equal to the final momentum. So if the initial momentum is 1, then the final momentum must also be 1. So the answer is going to be D. All right. So number 9 says we have an astronaut floating alone in space. He throws a baseball. He throws a baseball. If the ball moves away at 20 meters per second, the astronaut will move in the opposite direction, right? Well, he's actually going to move in the opposite direction at a 20 meters per second, a higher speed, a lower speed. More information is needed. Well, he's actually going to move in the opposite direction with a lower speed, right? And that's just going to be because he has way more mass than the baseball, right? So since he has more mass than the baseball, he's going to basically, float in the opposite direction at a lower speed. Now, if he had something more heavier, then that would be like a different case. But since the astronaut has so much mass, this is real similar to the, if you're standing on ice, basically exactly the same scenario. If you're standing on ice and you throw an object this way at some velocity of 10 meters per second, or 20 meters per second, however fast you throw that object that way, you're gonna go in the opposite direction, right? But you're not gonna go as fast as what you threw the object because you have more mass. So the answer to number 9 is gonna be C. Number 10, if you push for an hour on a stationary wall, you do no work. Well, we know work is basically given by force by distance, and since the distance is 0, then the work is going to be 0. So if you're pushing on a wall for an hour or however long and the wall doesn't move, you do basically 0 work onto the wall. So the answer to 10 is going to be B. So you do 0 work on the wall. All right, so number 11 says when you push an object a certain distance while applying twice the force you do. So if I make the force twice as much, then what's going to happen to the work, basically? Well, if I do 2 times the force, that's basically going to make the work twice as much, right? Because all we did now, if we look at these two, it's just multiply by 2. So you do twice as much work if you do twice the force. And same thing if you, push with the same force but twice the distance, then that would be twice the work. So for 11, it's going to be C. 12 says you have a music console and it's pushed by a force of 20 newtons. The work done on a console is, work equals force by distance. The force is 20 newtons. The distance is 2. So the work is going to be 40 joules. So for 12, the answer is going to be A. 13 says a shopping cart moves with the kinetic energy of 40 joules. So we have a shopping cart moving with some kinetic energy of 40 joules. And kinetic energy is given by 1/2 mv squared. If it moves at twice the speed, its energy is, if we double the speed here, let's double the speed, see what happens. So Now we have 40. Well, let me do it this way. So we have 1/2 m 2v squared, right? Because we doubled the speed. So now we have to square both of those. So now that becomes, that becomes 4, and becomes v squared. So now we have, I'm bringing the 4 right here to the front. 1/2 mv squared. Where this 4 basically came from squaring that 2, right? And then there's the v squared over there. And now we know we have a kinetic energy of, well, this is the same as that, right? So this part here by itself is 40. So now we have 4 times 40. That's going to give us 160 joules. So if we double the speed, it's going to increase the kinetic energy by 4 times, So the answer is going to be B. Let's see. When diver Danny, who weighs 500 newtons, steps off a 10 meter above the water, steps off a diving board 10 meters above the water, he hits the water with kinetic energy of, well, this is basically conservation of energy, right? Because there's no there's no energy leaving the system. So we could say initial energy equals final energy. His initial energy is basically related to his height. It's going to be mgh. And that's going to be equal to his kinetic energy. So his kinetic energy is going to be equal to his initial potential energy. And that's given by, well, mg is his weight. So that's going to be 500 times his height, which is 10. It's equal to 5,000 joules. So he's going to hit the water with 5,000 joules of kinetic energy. So the answer is going to be C. 15 says a circus diver drops from a high pole into water far below. When he is halfway down, A, his kinetic energy and his potential energies are equal. B, his potential energy is halved. C, he has gained an amount of kinetic energy equal to half his initial potential energy. Or D, all of the above. Or E, none of the above. So this one's actually going to be D, all of the above. Because we know, so we have some diver up here. Let's say this is halfway. That's the water. So up here, he has only potential energy, right? Because he's not actually, falling with any velocity yet. So once he gets halfway, he's going to have, well, the potential energy is going to decrease by half, right? So here he's going to have half the potential energy. And since he's falling with some velocity at this point, he's also going to have half his kinetic energy. And then once he reaches the bottom, it's going to be all kinetic energy. So up here, it's all potential energy at the top, all kinetic energy at the bottom, and in between, it's going to be half and half of both. So basically, they're going to be equal, so that's true. The potential energy is halved, that's true. And he's also gained some kinetic energy. It's equal to half the kinetic energy. So the answer to 15 is going to be all of the above. Number 16 says a 1 kilogram ball is dropped from a height of 2 meters, but only rebounds 1.5 meters after hitting the ground. The amount of energy converted to heat is, well, So let's say initially we dropped from this height here, and this height is equal to 2 meters. So the potential energy is going to be mass times g times height, right? So the mass is 1, g is 10, and that's 2. So 1 times 10 times 2. So the potential energy is going to be given as 20 joules. Boom. So this is how much energy the ball has when we drop it from that height. So we drop it, bounces and goes back up, only a height of 1.5 meters. So I'm gonna draw it right here. Goes back down, bounces back up to this height. But that height is only 1.5. So how much energy does it have at that point? Well, here, potential energy is gonna be 1.5, because that's the height, times g, which is 10, times, what else? The mass, which is 1. So that gives us a potential energy of 15, because it's just 1.5 times 10. So it's going to be 15. All right, so it's going to be 15. So basically we see here now that originally the energy was 20, and now once it goes back up to that height, the energy is 15. So the amount of energy lost is 5 joules. Well, that means 5 joules must be lost due to heat. And so that 5 joules between that difference must be equal to the heat there. So the answer is going to be, let's see. So the answer is actually going to be B, because there is no option for 5 joules, but they do have one that says more than 2 joules, and that would give us the 5 joules, because 5 is more than 2. So 16 is going to be B. 17 says the source of Earth's internal energy involves A, potential energy, B, radioactivity, C, the sun, or D, kinetic energy. Well, that's actually going to be B, radioactivity, because the Earth is slightly radioactive, meaning that it radiates. And so it's not going to be potential energy. It's not going to be the sun, because the sun is external to the Earth. And it's not going to be kinetic, because the Earth doesn't have it's just not going to be kinetic. I don't know how to explain that. So the answer is going to be radioactivity. 18 says the motion of particles that contributes to thermal energy are, well, this one's going to be translational, rotational, or C, vibrational. It's actually going to be all of the above. So let's say we have a balloon here, and we've got some molecules in there. And these molecules are moving around in all kinds of directions. So translational basically means left and right or up and down. That's what they mean by translational. So of course there's molecules moving up and down and left and right. Rotational basically means, a rotation or a spin. So of course, molecules can also be spinning around in here as well as moving up and down and left and right. And vibrational just means the molecules themselves are shaking like left and right. So of course the molecules can also be shaking because they're moving around in here. So the thermal energy is going to be a little bit of all of these, because the molecules are moving up and down, left and right, rotating and shaking. It's doing all those things. Number 19 says, on which temperature scale is 212 degrees the boiling point? A, Fahrenheit, B, Kelvin, C, caloric, or D, Celsius. Well, for one, it's not caloric because that's a temperature scale we did not even talk about. Let's see. We know it's not Celsius because Celsius says the boiling temperature of water is 100 degrees. And it's not Kelvin. And a way we can know that it's not Kelvin is because Kelvin is not measured in any type of degree. Well, never mind, forget that. It's not Kelvin because the boiling point for water in Kelvin is way bigger. I want to say like 300 and something. But for Fahrenheit, the boiling temperature of water is 212. And the boiling point for water in Kelvin is, let me see, is 373. All right, so the answer to number 19 is going to be A. Number 20 says absolute zero corresponds to a temperature of, so absolute zero is basically 0 degrees Kelvin in the Kelvin scale. And it's also negative 273 on the Celsius scale. So it's actually both of these. So the answer is going to be C. Number 21 says heat is A, thermal energy, B, radiant energy, C, temperature, or D, thermal energy flowing from hot to cold. Well, we know the equation for heat is given by this, right? And so basically this change in temperature is the flow. And so basically heat is the flow of temperature. So the answer is going to be D for 21, because heat is thermal energy and flowing from hot to cold. 22 says when you touch a piece of ice with your finger, energy flows, well, energy always flows from hot to cold. So it's going to go from your finger to the ice. Let's see, compared to a giant iceberg, a hot cup of coffee has A, the same thermal energy but a higher temperature. B, more thermal energy at a higher temperature. C, less thermal energy at a higher temperature. Or D, none of the above. Well, let's look at this equation for heat again. So we see basically heat also involves mass. So just kind of ignoring this temperature here, but if we look at the mass, because the iceberg is, huge compared to a cup of coffee. That would be like an iceberg. This small little thing here would be a cup of coffee. So it's true the cup of coffee would have a higher temperature, but let's see, less thermal energy at a higher temperature. Yeah, But the iceberg actually has higher thermal energy, because you can also think of, cold being a form of thermal energy. And this iceberg, since it's so massive, has more thermal energy than this small cup of coffee, even though the small cup of coffee has a higher temperature because of this M here that's in the heat equation. So this M is way bigger for the iceberg. So the answer is going to be C for number 2023. All right, about halfway done now. Let's see. So 24 says, the temperature of water rises when 1 calories are added. It will rise the same when 83.4 joules are added, 8.38 joules are added, or 4.19 joules are added. Well, since 1 calorie equals 4.19 joules, this basically means if we heat some water by 1 calorie, that's the same as heating some water by 4.19 joules. Just different units, but these do the same thing. So the answer is going to be C for number 24. Let's see. 25 says, when work is done by a system and no heat is added, the temperature of that system is going to increase, decrease, or remain the same. So let's say we have some system here. This is the system. And this system is doing some amount of work. So it's basically exerting energy, right? So since this system is exerting some energy in the form of work, it's basically going to lose energy because it's giving away some energy in the form of work. And so since this system is giving away energy in the form of work, the temperature of this system is going to decrease. So for number 25, the answer is going to be B. The temperature is going to decrease. 26 says, which law of thermodynamics addresses the direction of heat flow? All right, erase this. So let's see the 3 laws of thermodynamics. So it's laws of thermo. Well, the first law is just the conservation of thermal energy. The second law says basically hot air or heat goes from hot to cold. And the third law says no system can reach zero, absolute zero. And so for number 26, heat flow deals with the second law. So number 26 is going to be the second law. 27 says leaving a hot oven door open in a closed room on a cool day does what? Well, since we know temperature always goes from hot to cold, the hot oven is going to heat up the room. So number 27 is going to be A. It's going to increase the temperature. increase room temp. '28 says, as entropy in the system increases, energy within the system. Okay, does what? Well, remember, we could think of entropy. Entropy is basically the same as disorder. So as entropy increases, disorder increases. And so you can say, as entropy increases, so for number 28, as entropy increases, it becomes less ordered. So it becomes less ordered because entropy is increasing. So if entropy increases, then basically we're increasing the disorder. Or in other words, it becomes less ordered. So entropy is most closely related to A, the first law of thermodynamics, which is just the conservation of thermal energy, or B, the second law of thermodynamics, which is, heat goes from hot to cold, or C, both of these. Well, the answer is actually going to be B for 29. Answer is going to be B, the second law. Because you can kind of think of it like this. So as hot flows to cold, which is basically the second law, right? Hot always flows towards the cold. You can think of hot being basically disorder and cold being more ordered. Because as things are hotter, they're more wild. And so more wild means like more disorder, right? And so since things flow from disorder to ordered, this basically kind of shows the direction of entropy, right? Because we know something naturally, entropy is always increasing. So like if your room, if you don't clean it, your room's just going to naturally become more and more dirty or more disordered. And so that's basically kind of shows the direction of from hot to cold, which is not Newton's, but the second law of thermodynamics. All right, so let's see, number 30. Number 30 says a substance that heats up relatively quickly has a what? A high or low specific heat, a high specific heat, low specific heat. Well, specific heat is that right there, that C, right? So a good way to kind of remember this is water has a high specific heat, or has a high water has a high specific heat, right? Meaning that it takes a lot of heat in order to change the temperature of water. So if something has a low specific heat, then the temperature changes relatively easy. And so here, the answer is going to be, let's see, answer is going to be C, a low specific heat. So low specific heat, so low C basically means it heats up quickly. Heats heats up fast. But water, which has a high specific heat, takes, it heats up slow. So 31 says, after an apple pie is taken from the oven, the pie filling is hotter than the crust due to the high conductivity of apples, B, the uneven temperatures, or C, water in the filling retains thermal energy. So for number 31, the answer is going to be C. All right, because we know water, like I just said a moment ago, has a high specific heat. C for specific heat. So since the specific heat of water is so high, it takes a lot of energy to change the temperature, right? In other words, that also means water retains its temperature better than other things, so say a metal. So like, let's say we, have like a hot spoon, put the hot spoon on the stove, it heats up and gets hot. If you take that spoon off of the stove, it's gonna cool down, pretty quickly. And probably after a minute or so, you could probably touch the spoon, and soon after that, it won't be as hot anymore. But if you warm up water till it's really, really hot, let's say boiling, then if you take the water off the stove, then that water is gonna still be hot for a long time after. So meaning water retains its temperature better than, let's say a metal. So the answer is going to be C. Number 32 says, which will cool faster when removed from a furnace? Iron, silver, or the same? So number 32, the answer is actually going to be B, silver. Basically, it's going to be B, silver, because silver has a lower specific heat. So the specific heat of silver, and let's see the specific heat of iron. I'm not sure what the values are, but we know the specific heat of silver is lower, the specific heat of iron is higher. And so since the specific heat of silver is lower, that means the temperature changes a lot faster, right? Basically kind of like what I just said about water, because water has let's say specific heat of water is highest among these three things. So if you were to put all three of these things in a furnace, so we put some water, iron, and silver, put all three of those things in the furnace, and then take them out, the water is going to take the longest time to cool down because it has the highest specific heat. The iron is going to take the second longest because it has the second highest. And silver is going to cool down the fastest because it has the lowest specific heat. All right, hope that makes sense. Number 33 says, let's see. Says San Francisco has milder winters than Washington, D.C. due to water's high temperature in the Pacific Ocean, conductivity, or specific heat capacity. Well, B and C, neither one of those really make any sense, but we do know water has a high specific heat, right? So for number 33, then the answer must be A. So for number 33, the answer is A. 34 says, the operation of a bimetallic strip relies on differences in the heat capacity of metals, the conductivity of metals, or the expansion of metals. Well, the bimetallic strip was basically a strip that has two different metals on either side, right? Kind of like that. And then this strip gets heated up. And we know when things heat up, they tend to expand. Well, when a metal heats up, it tends to get longer. And that's given by, we know this equation here, alpha L delta T, where the change in the temperature, so if we change this metal by some temperature, the original length is going to change by this much. So this bimetallic strip basically works or relies on the differences in the expansion of metal, which is given by this little alpha here. So basically we would have this equation for the blue strip, and we'd also have the same equation for, again, but for the red strip, because this alpha is going to be different for the red versus than for the blue. So one of these metals is going to expand more than the other just because they're made out of two different materials. So 35 says a hot ring, an iron ring is heated, the hole becomes what? So hot ring here, if we heat this up, again, but from what I just said, whenever we heat up an object, it tends to expand. So if we heat up this ring, it's basically going to expand a bit because it's being heated up. So the hole is going to become larger. So number 35 is A. 36 says, during a very cold winter, water pipes burst because A, the thawing process produces pressure on the pipes, or B, water expands when freezing. Well, that one sounds right. Or C, ground contacts. Oh, the ground contracts when colder, pulling pipes apart. No. Or D, water contracts when freezing, or E, none of the above. Well, first of all, we know when water freezes, it expands. That's the basically strange thing about water when it freezes. When water freezes, it expands because of its structure. Right? So when water freezes, it's going to expand. And so since water inside the pipes are freezing, it's going to expand. And also when the pipes get cold, they're actually going to contract. And so we have the pipes contracting, and we also have the water expanding at the same time. That's basically what's causing the pipes to burst. 37 says, well, actually, let me write this out. 36 was B. 36 was B. 37 says ice has a lower density than water because, well, that's going to be E. Ice has a lower density because of its structure. So because ice expands when it freezes, so when water freezes, it expands, and it expands because of its structure, and also because it expands, it becomes less dense. So 37 is going to be E. Let's see, 38 says, when ice floats in water, melts the surrounding water level. So if you have a cup of ice here, and this water basically starts to melt, the water level is actually going to remain the same. So the answer to number 38 is going to be A. 39 says, which of these are good conductors? A, wood, B, snow, C, feathers, or D, none of the above. Well, basically a good conductor is something that heats up quickly, kind of like iron. Whenever you kind of think of a good conductor, think of something that has good flow. So we basically use iron as our skillets because iron is a good conductor, right? And so wood is not something that we cook with. We don't have wooden stoves. We don't have stoves made out of snow nor feathers. So the answer is going to be none of the above for 39. 40, the main reason you can walk barefoot on red hot coals. Red hot coals of wood without burning your feet involves what? The low conductivity of coals, mind over matter, low temperature of the coals. Well, this one is going to be because of the low conductivity. It's going to be because of the low conductivity of the coals, right? Well, low conductivity just means it doesn't transfer heat that well. And so you can walk over hot coals as long as you do it kind of fast. The heat won't transfer to your feet that well. 41 says the process of convection occurs in what? Well, the answer to that is going to be D, fluids. Convection is one of the 3 forms of heat transfer. Conduction is heat transfer through direct contact. And then there's also radiation, which is heat transfer through electromagnetic waves. And then there's convection, which involves basically heating things up or heat transfer through a fluid. Where air is air is basically a fluid. So whenever you hear convection, just kind of think of your oven. So the answer here is going to be D. .42 says, if you blow on your hand and you feel the warmth of your breath, you pucker your lips so your breath expands as you blow, and your breath is what? Well, when air expands, it becomes cooler, right? So as air expands, it becomes cooler. So that's why when you pucker your lips and you blow the air, your breath is actually going to be cool. So this is going to be cool. And I'm sure this is something we've all experienced. If you blow your breath like this versus, then you can obviously feel the difference. And that's basically due to the air expanding as you pucker your lips and blow. All right, so 43 says, radiant energy emitted by our planet is the outcome of radioactivity in the Earth's interior. Well, that's right, because that was one of the answers to an earlier question. the energy is electromagnetic. That's also true. And it's C, terrestrial energy. Well, we know that's also true. So 43 is going to be D. 45 says, after taking a shower and stepping outside the shower stall, the chill you feel is mainly due to what? Well, the answer here is going to be A, evaporation. Because after you step outside the shower, you basically have all this hot water on you. And then that hot water is also going to absorb even more heat from the surrounding environment, causing it to evaporate. And then that evaporation of that water is what's cooling you down. So this is basically the same way sweat kind of works. Once you sweat, you have water that comes on the surface of your skin, and then that water evaporates, allowing you to cool down. Let's see, 46 says, when a solid is changed to a liquid. So when a solid is changed to a liquid, energy is absorbed, released, or neither. Well, for a solid to become a liquid, energy has to be absorbed, right? So, like, let's say this is ice, energy has to be absorbed. So ice has to, because ice is a solid, ice has to absorb energy in order for it to become a liquid. So number 46 is going to be A. 47 says, steam burns are much more damaging than boiling water burns because A, it's gaseous, B, has a higher temperature, C, is hotter, or D, releases more thermal energy. Well, the correct answer here is going to be D. So number 47, answer is going to be D. And let me go to number 48, because 48 is going to kind of explain number 47. So number 48 says, which requires more energy? Changing 1 gram of 100 degrees Celsius water to 100 degrees Celsius steam, or B, melting a gram of 0 degrees Celsius ice, or C, increasing the temperature of 1 gram of water to 0 to 100 degrees Celsius, or D, all the same. So this basically goes back to a chart that I drew out, where this is the basically heat temperature chart. So as you go up, this is increasing the temperature, and as you go to the right, that increases the heat. And this looks something like this. Something like that, right? Where this region here is water. This region here is ice. And all this over here is steam. So last time I tried to describe this, I tried to point out here that basically the difference between here and here requires the greatest amount of heat. And this is basically trying to change water completely into steam. So this is evaporation. evaporation. And then this would be like fusion, because this is basically ice melting. So let's apply each one of these sections to these options here. So A says changing 1 gram of 100 degrees Celsius water to 100 degrees Celsius steam. So that's basically this part. So this part here describes A, because you're trying to change water into steam. Melting 0 degrees Celsius ice, well, that's this region. So this region is B. Increasing the temperature of water from 0 to 100. So that would be this one. This is C. So which one requires more energy? Or in other words, which one requires the most heat or the most Q? So if you look here, the difference between here to here is pretty small. So we know it's not C, or if no, it's not B. For C, it's a little bit more than B. I mean, I didn't draw it that way, but this is supposed to be a little bit bigger. But then if you look at the difference for A, which goes from here to here, because that's how much heat is required. So a lot more heat is required for evaporation than either one of these other two processes. So the answer to number 48 is going to be A. And I think that's about it for the review. I know that kind of took a while. It took longer than I thought, but hopefully this helped out. Yeah, hopefully this helped out. So yeah, just again, go through the problem. Just make sure you understand each one and why the answer is what it is. And yeah, good luck on your test this week.